In this video, we're going to talk about the 9.2 notes, which is all about concavity and inflection points. So we talked very briefly about concavity back when we were introducing the second derivative test back in topic 8, but now we're going to go actually into detail about what concavity is, so concave up and concave down. We're going to define what those are. We're going to talk about what an inflection point is and how that relates to concavity, and then we're going to talk about yet another test, the concavity test, to determine where a function is concave up or concave down. So in most of the recent sets of notes, we kind of took a little side detour when we were talking about optimization in the previous set of notes. But for the past several notes, we've been talking about how we can use calculus to describe features of functions. So we talked about where the function is increasing or decreasing, and we talked about finding two different types of extrema, local extrema and absolute extrema. So these features, increasing and decreasing intervals and extrema, give us quite a bit of information about how a function behaves and related to that, how it looks on a graph. But there are still some pieces of information that are missing. Now just look at an example here to kind of emphasize what might be missing from all of this information that we can already get about a function. So let's say we have a function that's increasing on the interval from 1 to 4 with an absolute minimum at x equals 1 and an absolute maximum at x equals 4. And we want to maybe figure out what this function looks like. So these are all terms and features that we're familiar with, right? We know what it looks like for a function to be increasing, we know what an absolute minimum represents, and we know what an absolute maximum represents. So how could we draw this function? So if I consider the interval from 1 to 4, I have an absolute minimum at x equals 1, so that's somewhere here, and an absolute maximum at x equals 4. And so I know my function is increasing, has a positive slope from 1 to 4. So a possible way this function could look is this. If I could actually draw, let me draw that better. Another way this function could look, with the same parameters, the same features, if I draw those endpoints exactly the same, another way this function could look is maybe like this. It's still increasing, it still has, again, if I could draw a positive slope from 1 to 4, so it's still increasing on that interval. Or maybe I could have something like this. So if I consider again the interval from 1 to 4, same endpoints, maybe my function is doing something like this. Where again, it's got that positive slope, it's increasing, it's got an absolute minimum and maximum at 1 and 4 respectively, but it looks like there's some other features that we haven't yet discussed that might define a little bit more precisely what the function is doing between 1 and 4, or how it looks between 1 and 4. And so we're going to talk about two additional features that help us a little bit better pinpoint how the function is behaving, in addition to whether it's increasing or decreasing, or where its local or absolute extrema are. We're going to talk about concavity, and we're going to talk about inflection points. So that's the focus of this set of notes. So like I mentioned, we briefly talked about concavity when we were introducing this idea, or back in the 8.2 notes, we briefly talked about concavity when we were talking about how to identify local extrema using the second derivative test. And so a lot of this is a little bit of review of the second derivative test and this definition of concavity. So if we go back to the 8.3 notes, when we were talking about intervals of increasing and decreasing, we talked about how we could use the first derivative to determine increasing and decreasing for a function. So this was the general definition of increasing and decreasing on an interval that we introduced back in the 8.3 notes. But the way that we focused on it and the way that we tested for increasing or decreasing intervals was by considering the sign of the first derivative. Function is increasing on an interval if the first derivative is positive, strictly greater than 0. And a function is decreasing on an interval if the first derivative is strictly less than 0, negative on an interval. Now, concavity, as we sort of saw in the 8.2 notes, relates to the second derivative. And so when we talk about concavity, sort of the visual representation of the second derivative, we're talking about describing how the first derivative is changing. So rather than how the function itself is changing, concavity uses the second derivative to describe how the first derivative is changing. Is the first derivative positive? Is the first derivative negative? And not only that, but how is it changing? What is its slope doing? What is the slope of the first derivative doing? That's this idea of concavity. So concavity, like I mentioned, is tied to this second derivative, and concavity is like the visual result of the behavior of the first derivative in terms of what the slope of the first derivative is doing. So if we consider concavity, we have two different ways we can describe the concavity of a function. We can talk about a function being concave up, or we could talk about the function being concave down. So let's start with concave up. A function is said to be concave up on an interval if the function lies above all of its tangent lines on that interval. So let's visualize that here. Let's say I have a graph. Let's say my interval is from, let's just say, a to b. And maybe I have a function from a to b that looks like this. Actually, let me make that curve a little bit sharper so it's easier to draw on it. There we go. I'm going to miss that when we get back in person and I have to draw in pen. So what does it mean for the function to lie above all of its tangent lines? Well, if I think about this function and I think about the tangent lines to this function, if I just pick a couple points, I can see that there's my tangent line there, there's my tangent line there, there's a tangent line, there's a tangent line. We can see that the tangent lines are sitting below the function. In other words, it's like the tangent lines are cradling the function. They're holding the function up. What this represents in terms of the first derivative is it means the first derivative is increasing. Its slope is getting steeper, and visually that translates into this concave up shape. Concave down is just the opposite. If we have the same sort of a thing, a function on an interval from a to b, we say that this function is concave down if the function lies below all of its tangent lines on that interval. So if we had something like this, here's our function f of x, and we think about its tangent lines. So here I drew the tangent lines in red. Here I'll draw them in, I don't know, blue. If I pick just a couple points on this function, here's my tangent line, here's a tangent line, here's a tangent line. We can see that in this picture, the tangent lines are sitting on top of the function. So now the function is like holding up the tangent lines. Here it's like the function's cradling the tangent, or the tangent lines are cradling the function. Here it's like the function is holding up the tangent lines. This would be concave down. And visually, what this means in terms of the first derivative is decreasing. The slope of the first derivative is getting less and less and less. Now, I will be posting like an extra supplement, kind of like I did with the trig functions and the chain rule and things like that, because once we start getting into the second derivative, sometimes people have trouble thinking, okay, well, what does it mean for the second derivative to describe the change of the first derivative? What's the derivative of the derivative? What does that mean? What does that look like? So I will be posting more information on this if you're curious about like the visual representation of the function versus the first derivative of the function versus the second derivative of the function, because they can all give you different information about how the actual function is working. But for now, in terms of concavity, it's more about just thinking about it visually. So if we think about what it looks like for something to be concave up versus concave down. And the way I always think about it is concave up makes a cup. My stupid little rhyme for this, everybody always hates it, but I think it's effective. It makes a cup, so it's like cupping. If you were to dump water down, it would collect in the cup. Concave up makes a cup. Concave down, I say, makes a frown. So it's like an upside down, it's like a sad face. If you were to pour water on this, it would just slide off, acting like a little umbrella if there was somebody under here. That's how I remember concave up versus concave down in terms of how it looks. So up makes a cup, down makes a frown. Cup cups the water, frown, the water just falls off if you were dumping water down on top of the picture. Just a way to remember kind of a mnemonic sort of to remember what it looks like for something to be concave up or concave down. Okay, so we're going to talk about concavity visually here in just a second, because again, I think it helps to talk about it visually first. But I also want to introduce the concavity test, which is actually a really nice, easy test, similar to our increasing-decreasing test. But now instead of looking at the sign of the first derivative, we look at the sign of the second derivative. We use the sign of the first derivative to determine increasing and decreasing for a function. We look at the sign of the second derivative to determine concavity. So a function is concave up on an interval if the second derivative is positive on that interval. So in other words, if the second derivative is greater than 0, we have a concave up shape. So something like this or something like this. Function is concave down on an interval I if the second derivative is less than 0, negative on that interval. So we might have a concave down shape like this or like this. So we'll use this test in a couple examples on the next few pages. But the first thing I want to do here, just to kind of go off of what we were just talking about with visualizing concavity, let's take a look at that function that we used to sort of introduce extrema back in topic 8. And now let's use this to determine where this function is concave up and concave down on the interval from -4 to 5. So in other words, on this picture, on this chunk of the function, where is it concave up and where is it concave down? So for concave up, again, a couple ways to think about this. You can think about it in terms of the tangent lines, or you can think of it in terms of that cup versus frown. If I consider what's going on between -4 and, let's say, this point here at -1, it looks like I have that cup shape. And if I were to draw some tangent lines in here to this function, I would see, and I'm kind of drawing them away from the function just for emphasis sake. Of course, the tangent lines do touch the function, but just to emphasize where the tangent lines are, it looks like my tangent lines would cup or hold up this function. So they're sitting below the function, which indicates that on this interval, the function is concave up. So concave up on the interval from -4 to -1, it looks like. What about concave down? So concave down makes a frown, or it's like an umbrella. If you were to dump water from the top of this picture down, concave down would shade you rather than cup the water. And so if we think about concave down, it looks like from x equals 2 all the way to the end there, x equals 5, it looks like we have a concave down sort of a shape. It's acting like a little frown, a little umbrella, and again, if I were to draw some tangent lines in here, it looks like the tangent lines would be sitting on top or above the function. So it looks like I have concave down from -2 to 5, it looks like. Now, an interesting thing about this particular function is what's going on between -1 and 2, so this straight line here. Well, if I were to draw the tangent line to this diagonal line here, it would sit directly on the function, right? So the tangent line is actually going to be exactly equal to the function along here. It would sit exactly on the function. And all that would mean is the function is neither concave up nor concave down. So when you've got sort of like a straight piece of a function like this, where the tangent line sits exactly on the function, on the diagonal piece in this case, it just means that the function is neither concave up nor concave down there. So I'll say here, neither concave up nor concave down on, what is that, the interval from -1 to 2. So just visualizing concavity a little bit there. Now the last thing I want to mention here before we get into some actual examples where we assess concavity just from the function rather than a graph, I want to talk about inflection points. So we say point C is an inflection point if the function is not only continuous at C, but the function changes concavity at that point. So it either changes from concave up to concave down or vice versa. So essentially, to assess where we have inflection points, we look to see where the second derivative is 0. So if f prime prime of C is 0, then C is a potential inflection point. It doesn't necessarily mean that C is actually an inflection point. We do need to check and see if the concavity changes at that point. But our potential inflection points occur when the second derivative is 0. This is very similar to how we used critical points when we were talking about extrema. So if I go back to extrema here and I introduced the critical points way back on page 2, we mentioned that critical points and singular points technically were both candidates for local extrema. It was up to us to determine if those points were actually local extrema, but essentially listing the critical points and the singular points gave us a list of potential local extrema. It's the same sort of thing here. Listing where the second derivative is 0 gives us a list of possible inflection points. And we just need to check and see if concavity actually changes across that point to determine if it is actually an inflection point. So we'll see some examples of that here as we go. Okay, so we've got concavity and we've got this idea of inflection points. And we also have, if we go to the top of page 4, yet another set of steps that we can use to determine concavity and inflection points. So we're going to go ahead and use these steps in this example here on page 4. So our function here, f of x, is x times e to the x. And we want to determine where this function is concave up, where it's concave down, and if there are any inflection points, we want to state what those are. All right, so if I take a look at my steps, I can see I have the second derivative here mentioned quite a bit. So first thing I'm going to do before I start these steps is I'm going to go ahead and find my second derivative so that I can use it in my process. So to find my second derivative, I need to first find my first derivative. So I'm going to go ahead and use the product rule here. I have x times e to the x, so a product of functions of x. And so my first derivative is going to be x times the derivative of e to the x, which is e to the x, plus the derivative of x times e to the x, which gives me a first derivative of x times e to the x plus e to the x. Now our second derivative, remember, is just going to be the derivative of the first derivative. So now I need to use the product rule for this piece and then add the derivative of e to the x. So derivative of this piece, x times e to the x, is x times the derivative of e to the x, which is e to the x, plus the derivative of x, which is 1, times e to the x. That's me using the product rule for this piece here. And then I have to add to that the derivative of just plain old e to the x, which is just e to the x. So this gives me x times e to the x plus e to the x plus e to the x, which I can write as x times e to the x plus 2 e to the x. And now again, I'm going to have to do some stuff with this second derivative, so to make my life a little bit easier once I start working with it, I'm going to factor out that common e to the x, and write this as e to the x times x plus 2. That might be a little bit easier to work with as I go forward. So this, I'll just put a box around it. This is my second derivative. So now let's actually look at our steps. Step 1. I want to find any possible inflection points by setting that first derivative equal to 0 and solving for x. So I'm going to take e to the x times x plus 2, set it equal to 0, and solve for x. So there's two ways this could be equal to 0. E to the x could be equal to 0, and x plus 2 could be equal to 0. Well, for e to the x, there is no value of x that I can plug in there to make that equal to 0. E to the x is always positive. So that piece is not going to get me a 0. But x plus 2 could definitely equal to 0 if x is equal to negative 2. So I'll put a box around this. This is a possible inflection point. So inflection points are places where my concavity might change, so I need to make note of those. In step 2, I actually also want to make note of places where the second derivative is undefined. So these are not singular points. Singular points are where the first derivative is not defined. But this is like singular points in the sense that I want to figure out, are there any places where the second derivative does not exist? Because technically, places where the second derivative cannot exist are also places where concavity might change. We'll see that later. So in step 2, where is the second derivative undefined? Well, our second derivative is this thing, e to the x times x plus 2. There are no values of x that would give me like a 0 on a denominator or a negative under a square root. So I can say here the second derivative is defined for all values of x. So there are no values of x where the second derivative is undefined. Okay, now we start to get, again, kind of similar in terms of what we're doing with what we did with intervals of increase, decrease, and when we were using the first derivative test to determine local extrema. In step 3, we use the points that we found in steps 2 and 1 to create intervals on our function. So in step 3, here's where I draw my little number line, and I'm going to put on this number line all of my potential inflection points from step 1, and any points where my second derivative is undefined. Well, my second derivative is defined everywhere, and there's only one possible inflection point, negative 2. So I'm actually going to have a pretty boring number line here. It's just going to give me two intervals. This interval, x less than negative 2, and this interval, x greater than negative 2. And then in step 4, we do our same sort of a process where we look at these intervals. But now, since we're interested in the sign of the second derivative to assess concavity, we check the sign of that second derivative on each interval. So now we use this, and we check the sign of this on however many intervals we've got. So I'll start with the left interval. For values of x less than negative 2, I'm going to choose a value of x. I'm going to pick negative 3, and I'm going to plug it into my second derivative. So I'm going to plug it into this thing up here. E to the negative 3 times negative 3 plus 2. And again, I don't care what this actually equals. I just care about whether it's positive or negative. So let's see. E to the negative 3, e is always positive. E to the something is always positive. Negative 3 plus 2, that's negative. So we're going to have a positive times a negative, which gives us a negative second derivative on that interval. For our second interval, x greater than -2, I'm once again going to pick a value on that interval and plug it into my second derivative. Zeros on this interval, nice easy number to work with. And so if I plug that into my second derivative, I get e to the 0 times 0 plus 2. E to the 0 is 1, which is positive. 0 plus 2 is 2, which is positive. So we're going to have a positive second derivative on this interval. Now, finally, what I can do is I can state my conclusion. I have noted where my second derivative is positive and negative. And so by the concavity test up here, I can say that my function is concave up where my second derivative is positive, and concave down where my second derivative is negative. So for my conclusion here, I'm going to say by the concavity test, my function f of x is concave up on my blue interval, my interval where my second derivative was positive, which is from -2 to infinity. And concave down on the interval that was red, which is the interval from -infinity to -2. Now that's not quite all that we wanted. We also wanted to state any inflection points. So remember, an inflection point is a point where my function is continuous and is the place where my second derivative is 0 and the concavity changes across that point. So the place where my second derivative was 0 was x equals -2, and we just saw that my concavity does in fact change from negative to positive across x equals -2. So I can say here also, f of x has an inflection point at x equals -2. So here's my conclusion. Now, visually, what does this look like? Here's good old Desmos. Oops, ignore the e to the x there. Here's the function, x times e to the x. This is the one we were just looking at. And we said that this function is concave up on -2 to infinity and concave down on -infinity to -2. -2 is an inflection point. So if we take a look at this function, we can see here's -2, that point there. And if we think about what's going on to the left of -2, we can see we've got that very slight concave down. That frown shape is very, very slight, but it is concave down from -2 to -infinity. And then once I hit -2, then I start seeing that cup shape. Zoom in here a little bit more. So from -2 and beyond, there's that concave up shape, the cup. And so -2 is the inflection point where that concavity changes from concave down to concave up. So that's visually what this looks like. Let's do a couple more examples. So this one is a pretty easy one, but it's worth looking at just to mention a little bit more about inflection points. So for this example on page 5, we have a nice simple function, f of x is x to the 4th. And we want to determine where this function is concave up, where it's concave down, and state any inflection points if they exist. So the function x to the fourth is very similar to the function x squared. So if you know what x squared looks like, it's pretty much what x to the fourth looks like. And so you might already be able to say, oh, I know what the concavity is, and I know what to say about inflection points. But let's just emphasize a little bit about inflection points here, just to mention some of the quirks about this idea of an inflection point. So first thing, I know I'm going to have to be dealing with my second derivative, so let's go ahead and find the first derivative and then find that second derivative. So f prime of x using the power rule is 4x cubed. And the second derivative, f prime prime of x, is the derivative of 4x cubed, which is going to be, using the power rule, 12 times x squared. And once again, I'll put a little box around that to emphasize that is our second derivative that we're going to be working with. So step one, just like we did up here, I'm going to find any possible inflection points by setting that second derivative equal to 0 and solving for x. So 12x squared equals 0. This is a pretty boring function to work with, pretty boring second derivative. The only way this can be equal to 0 is if x equals 0. So x equals 0 is a possible inflection point. Step 2 is figuring out if there are any points where the second derivative is undefined. So here, where is the second derivative undefined? Well, our second derivative is a polynomial, so it's going to be defined for all values of x. So there's no values where this second derivative is undefined, so we once again don't have to worry about that. We'll see an example where we do have to worry about that in a second, but we don't here. Step 3, again, this is that visual step where we just use the points in steps 1 and 2 to create intervals on our function. And once again, like the previous example, we only have one possible point to worry about here, x equals 0. So we're once again going to have a pretty boring little number line here that is split by this point, x equals 0. And so it looks like in step 4, we're going to have two intervals to assess. So step 4, like we did above, this is where we check the sign of the second derivative on each interval. So let's check the red interval first for values of x less than 0. I'm going to choose -1 as my value to plug into my second derivative. So again, plugging it into here, 12 times x squared, that's going to be 12 times -1 squared. -1 squared is 1. So if we think about the sign of this, 12 is positive, -1 squared is positive. So we have a positive second derivative on this first interval. For values of x greater than 0, same idea. I'm going to choose +1 to plug into my function, or to plug into my second derivative. So I have 12 times 1 squared. And again, 12 is positive, 1 squared is positive. So it looks like my function's second derivative is also positive on that second interval. So what can I say about this particular function's concavity? So by the concavity test, my function f of x is concave up on these two intervals. So specifically, on the interval from negative infinity to 0. And, using the little union sign here, the other interval, 0 to positive infinity. Which means it's not concave, and I'll just say it here, and is never concave down. Now, two things to mention here. First, this. A question I've gotten in the past about this is, can we just say it's concave up everywhere? So why can't we write it like this? We can't write it like this because for concavity, specifically for concave up, let me go back up to its definition. A function is concave up if its second derivative is strictly greater than 0. And what we did here, and this is part of what we do step 1 for, is step 1 showed us where that first derivative or that second derivative is 0. So technically, when x equals negative 2, the second derivative is 0, meaning that we don't have down here, where our second derivative is 0, happens at 0. Because that's where we said, sorry, I was looking at the wrong example, that's where we said our second derivative is equal to 0. And so technically, at 0, we don't have a concave up function. We have a function that's neither concave up nor concave down. So we have to express this excluding 0, meaning we want those two open intervals that don't include 0. So in other words, this statement would be incorrect because technically at 0, the function is not concave up. So we want to make sure we write it like this. Now, the second thing I want to mention has to do with the second part this question asks. State any inflection points. So we did find a place where where the second derivative is 0. But remember with inflection points that, go back up to that definition here, places where the second derivative is 0 they are potential inflection points. We need to see if concavity changes at that point. If it doesn't, it's not technically an inflection point. So if we consider this example, let me scroll to the correct one. At 0, that's a possible inflection point, but notice that the inflection or the concavity doesn't change. It stays positive across 0, which means 0 is not technically an inflection point. It's a place where a inflection point might be, but for this particular function, technically it's not an inflection point. So for this example, there are no inflection points. So I'll say also, there are no inflection points. Now the graph for this is pretty boring, but let's take a look at it anyway, just to confirm. Here's x to the 4th. It's just kind of a fatter x squared at the bottom there. So at x equals 0, we said that's where our second derivative is equal to 0. And we can see that on either side of 0, we've got that cup shape. And in fact, this whole function just makes a big giant cup. It is concave up everywhere except at 0. So it's a pretty boring function to look at, but it's useful for emphasizing how we need to be careful writing the intervals of concavity and how we need to be careful about our definition of an inflection point. So even though it's a kind of a boring example, it's a good one. It's a useful one. All right, let's do one more. Page 6. So here our function is x over x plus 1. And once again, we want to figure out where this function is concave up, where it's concave down, and if there are any inflection points, we want to state them. So let's start by finding the first and second derivatives, since I know I'll need the second derivative as we go forward. All right, so it looks like we have a rational function here, so we're going to need to use the quotient rule when we take the first derivative. This is going to be our denominator times the derivative of our numerator minus our numerator times the derivative of our denominator over the denominator squared. So that's x plus 1 minus x over x plus 1 squared, which gives us a first derivative of 1 over x plus 1 squared. Now I'm going to need to take the derivative of this to get my second derivative, so I'm just going to make my life a little bit easier so I don't have to use the quotient rule again. I'm just going to write this as a expression with an exponent. So 1 over x plus 1 squared is equivalent to x plus 1 raised to the negative 2, which makes taking this second derivative a little bit easier. I can just use the power rule, technically with the chain rule. So with the power rule, I have negative 2 times x plus 1 to the negative 2 minus 1 times, this is like my inner function, x plus 1, derivative of x plus 1 is just 1. So we get negative 2 times x plus 1 to the negative 3. Now I'm going to need to do some stuff with this. This looks relatively simple as it is, but in terms of like finding where this thing is going to be equal to 0 or where it's undefined, I think it's easier to look at it as a fraction. So with taking derivatives, I like to get rid of the fraction. With working with the second derivative, I want to put it back in a fraction because I think it's a little bit easier to see what values make it undefined or what values might make it equal to 0 in a fraction form. So this x plus 1 has a negative exponent, so I'm going to go ahead and put that as a denominator, x plus 1 to the positive 3. And then this negative 2, I'm just going to put that as my numerator. So this thing is going to be my second derivative. So now we can go through the process. Step 1 is where I find all possible inflection points by setting the second derivative equal to 0 and solving for x. So I'm going to take negative 2 over x plus 1 cubed, and I'm going to set that equal to 0. Now, if I multiply both sides by that denominator, I get negative 2 equals 0, which can't happen. There's no way I can make negative 2 equal to 0. So this is something we haven't run into yet, at least recently, is a case where I cannot make the function or the derivative or the second derivative equal to 0. So here I'm basically saying there are no values of x such that the second derivative equals 0. And that's fine. All that means is there's not going to be any inflection points. We don't even have any candidates for inflection points because there's no possible place, no value of x that would make that second derivative equal to 0. And those are the only points that could possibly be inflection points. So the consequence of this is just that there will not be any inflection points. There are no inflection points. Okay, so we checked inflection points. There aren't any, but we still want to check in step 2 where the second derivative is undefined, because these are still places, even though these are technically not places where we could have inflection points, they are places or values of x where the concavity could change as we cross that value. So I'm once again here in step 2 going to figure out where my second derivative is undefined. So where is f prime prime of x? Undefined. So if I take a look at my second derivative, this is part of why I like to put it back in fraction form, because it's a little bit easier for me to see in this form versus this form, at least personally, what values would give me trouble with this structure. So this is a rational function. So what would give me trouble is something that gives me a 0 on my denominator. And if I look at the thing down in my denominator, I have an x plus 1. If I have negative 1 in there, I have negative 1 plus 1. That gives me 0. So my second derivative is undefined at x equals negative 1. So what that means in step 3 is even though I don't have any technical inflection points, when I draw my number line, I'm still going to consider this point where my function's second derivative is undefined because technically this is a point where concavity could change as we cross that point. It's not technically an inflection point, but it might be a place where the sign of the second derivative changes, which would mean concavity changes across that point. So I am going to want to use that to divide up my number line into, once again, 2 intervals, where, as we've seen a couple times now in step 4, I assess the sign of my second derivative on these intervals. So let's start with our usual left-hand interval here for values of x less than negative 1. I'm going to use a function value of negative 2, and I'm going to plug that into my second derivative. So my numerator is negative 2. My denominator is negative 2 plus 1 cubed. So negative 2 is always going to be negative on my numerator. Negative 2 plus 1 is negative. Cubed, it's still negative. So that's going to leave me with a positive second derivative on this interval. For my second interval, x greater than negative 1, I chose 0 as my function value. And plugging that into my second derivative gives me negative 2 over 0 plus 1 cubed. Negative 2 is always negative. 0 plus 1 is positive. Cubed, it's still positive. So we have a negative second derivative. A negative divided by a positive is going to give us a negative. So now I can use my concavity test to state my conclusion. So by the concavity test, my function is going to be concave up on the interval where I had a positive second derivative. That was my red interval. That interval is negative infinity to negative 1. And concave down on, in this case, my interval where my second derivative was a negative, which is the blue interval, negative 1 to positive infinity. So notice I'm not including the negative 1. Technically, the negative 1 is not an inflection point because it is not a place where the second derivative is defined, or more specifically, where my second derivative is 0. It's actually a place where my second derivative is undefined. Because my second derivative is undefined there, I don't want to include that in my intervals here because I can't assess concavity where the second derivative is not defined. So I can't assess it at negative 1. So I don't want to include it in either interval, hence the open brackets. It's also not an inflection point. It is technically a point where my sign of my second derivative changes. So as I cross over negative 1, my concavity changes from up to down. But technically, inflection points can only occur at places where the second derivative is 0. So even though I've got this sign switch in my second derivative as we cross negative 1, even though my concavity changes at that point, it's not a place where the second derivative is equal to 0. It's just a place where the second derivative is undefined. And so it's technically not an inflection point. So I can say also there are no inflection points. So there's my answer for this one. And again, if we visualize what's going on here, so that was the previous example, here's this one. X over x plus 1 looks like this. So we could see that x, that negative 1, technically is also where the original function is undefined, right? So here, negative 1, the function is undefined. It's actually a vertical asymptote. And we can see that to the left of x equals negative 1, we have that cup shape, concave up. And to the right of negative 1, we have that, it looks kind of weird, but it's that frowning shape, that concave down shape. And again, negative 1 itself is not an inflection point because the function, as well as the function's second derivative, is not technically defined at negative 1. So because the second derivative is not defined at negative 1, we can't say anything about concavity there. And because the second derivative is not equal to 0 there, it technically cannot be an inflection point. So even though the sign of the concavity changes as we cross that point, by the definition of an inflection point, this value does not meet that definition, negative 1, so it is not an inflection point.